Let's look at this again briefly. So we wrote the total derivative in terms of the partial in time and space derivatives. And of course, when you carry these non-Cartesian, you have complicated expressions that include geometric terms. And that becomes more obvious here, reminding ourselves that the distance from the center of the Earth to the height in the atmosphere or ocean is the radius plus z, where of course the radius of the Earth is much greater than the height above or below the surface, which means r is essentially equal to a, in which case a is constant, so dr just becomes dz, the local vertical. And in that case, the acceleration term has minus 1 over rho a cosine phi dp d lambda plus 2 omega v sine phi, which is the vertical term, and you have minus 2 omega cosine phi, which is the horizontal term. So we have kept the terms of Coriolis here. This is the geometric terms with an overbar. So just for convenience, the meridional, the horizontal, vertical, and geometric terms are being shown with 1 underbar, 2 underbars, and 1 overbar. So this is the geometric term again, and the frictional forces or dissipation forces. Okay, as I said, just remember that you can find the equations in the book, but just get comfortable with them so that you remember all the terms, even if you cannot derive them by yourself. So you should always be able to interpret the equations. Okay, that's the main goal, so that it makes clear that you have understood the physics that's represented in the equations, not necessarily be able to derive them from scratch. Physics is the hardest part always. dv dt equals minus 1 over rho dp dphi. So we are writing now the zonal, meridional, and vertical terms separately. You have again the horizontal, geometrical, and vertical terms. Here it's vertical and geometrical, of course. Dissipation or friction in the vertical, we will soon see that the balance can be reduced essentially to minus 1 over rho dp dz equals minus g when there is no friction and when the scales of motion in the vertical are such that these terms can be dropped. So it's a matter of who's balancing who. And then the question is, we keep talking about convection in the tropics, which you would assume is a very fast vertical motion, almost the same scale as horizontal motions, let's say tenths of meter per second. Then can the balance still be between pressure gradient and gravity? Remember, pressure is high at the surface, decreases as you go up, so it's pointing, pressure gradient force is pointing upwards, gravity is pointing downwards. If they can balance, that's what is hydrostatic balance, right? The continuity equation looks like this with the longitudinal and latitudinal terms and vertical term, of course the geometric terms as well. I'm not going to read them because they are kind of complicated, so you just have to be able to look at them and realize what they are. So the scaling of the atmospheric motions in the tropics requires certain non-dimensional numbers. So we will use the definition of parameters described here along the derivations and discussions we will have throughout the course. So it's better if you can remember these. These are really important ones. The last four quantities are formed here as ratios in terms of governing equations. So scale height, g. RT0 over g, it's a vertical e-folding depth of thermodynamic variable. Brunt-Vesala frequency is a frequency of oscillation in a stably stratified fluid. So if you have a stable stratification with light density on top of heavy density, and some perturbation comes along and moves a parcel up or down, then the buoyancy and the gradient is going to determine the oscillation. So you can see that that's in terms of the potential temperature and the gradient, vertical gradient of the potential temperature. Static stability is fairly straightforward. dln theta dz. It's better done as ln theta because theta has that exponential term. So if s is greater than 0, you have stable stratification. If s is less than 0, you have unstable stratification. Rossby number, which is one of the important numbers we will discuss a lot, is essentially a ratio of inertial and rotational terms. It is, we'll see, turns out to be very important for various scalings in the extratropics versus the tropics. So how large are the inertial terms with respect to the rotational constraints? That's going to determine how the flow is going to be balanced. And Froude number is the ratio of fluid speed to the gravity wave phase speed, u squared over gd. The perturbations in the system in the atmosphere and ocean are often radiated out as gravity waves. I hope you all remember the basics. When we say gravity wave, gravity is the restoring force. So for waves, we need a perturbation force and a restoration force. So gravity wave has gravity as the restoring force. Richardson number is the ratio of potential and kinetic energies. We will see that even in the ocean, when you have vertical shear, for example, it represents stored potential energy, and if it tips over, then it converts into mixing and kinetic energy. So Richardson number is a critical number as well. Radius of deformation is the scale at which rotational effects become equal to buoyancy or gravitational effects. Remember, buoyancy is vertical and gravity is also vertical. So Rossby radius of deformation turns out to be also another important non-dimensional number, defined in terms of the Brunt-Väisälä frequency, the scale height, and Coriolis effect. F is the local vertical projection of Coriolis, so essentially 2 omega sine phi. Okay, that's what it is. We will get used to F being the Coriolis effect. Reynolds number, of course, comes even in the lab flows, small scale flows. It's a ratio of inertial to viscous forces. Again, when you want to compare atmospheric flows or ocean flows to lab flows, these are the numbers that really help. Ekman number is very particularly important for the ocean, where the friction is an important way, important process by which atmosphere distributes energy into the ocean. Words skip my mind sometimes. So that's AZ divided by FD squared, where AZ is a vertical eddy viscosity. So at these large scale flows, the dissipation is not happening so much at the molecular scale, but it's happening at the large scales where eddies dissipate energy, or they move it from one scale to another. There are processes where there is also upscale energy transfer, but when we say eddy viscosity, it is, let's say, moving the energy from the large scale background flow into the smaller scales and so on down, then to dissipation ultimately by friction at molecular scales. Okay, so looking at the equations in terms of P as a local difference of pressure along a horizontal surface. So you imagine a large scale pressure surface, then you have a perturbation P, and FR here is a measure of the observed frequency of perturbation in the atmosphere. Okay, it could be the various time scales we talked about in terms of synoptic, low frequency and high frequency intraseasonal time scales and so on. Those are the observed perturbations, and then you have the natural frequency F given by the Coriolis. Okay, so when we come back, we'll look first at whether hydrostatic assumption is valid in the atmosphere despite the fast vertical scales in the convection. right? Because if you remember your vertical momentum equation, then you have to drop the vertical acceleration terms along with some other terms for pressure gradient to balance gravity. Pressure gradient upwards, gravity downward. But if you have fast vertical motions, then how can you justify hydrostatic balance? We will see that essentially it is justified even when there is these fast convection processes.